This meeting is being recorded.
Okay, before we start in on the new topic, I just wanted to quickly look at from the chat a few of the wildcard highlights we didn't get to. We can take just a minute on this. Wooderjet, what did you do?
Yeah. So for wildcard week, I used the Warjack cutter to cut through 3 ceramic panels and 1 glass panel to create sort of a mosaic image.
Good. What was your Wazer experience?
I absolutely love the Waterjet cutter. It was actually the first machine I used when I first discovered the Fab Lab to make medallions, and very simple. It cut through ceramics beautifully, so I'm definitely gonna go back to it at some
Great.
point.
Yeah, no, it's nice. It's 10 rather than $100,000. And just to be aware, the more expensive machines are higher pressure, which means they use less garnet, but it's a good trade-off to have this accessible machine. Okay, yeah, I mean, and they're miraculous. They cut through anything.
Yeah, it's fantastic. I could have upped the strength on the glass. It didn't go entirely all the way through, so that'd be something to keep in mind for next time.
Ricardo, the cutting process itself isn't noisy at all. Really, the noise is just the pump. It's not a loud machine. Okay, nice. And then Maria, you did plasma cutting?
Sorry. Yes, I did plasma cutting and welding. For this week, I made a basket from wastes that I found in factory where we went last week. So I welded these parts and made a basket. And after I found valves and welded it too as feet for my basket. And I get this.
Great. Nice you have all of that available to you.
Yeah.
And then Isan did soft robotics.
Yes. Okay, hello. Yeah, this week we tested some soft robotic actuators. We use silicon for made the actuators and also syringe to inject the air and control the movement of the.
Nice. And yeah, once again, once you've done molding and casting, you know how to make soft robotics. And then great, and then so this is a classic use to make a gripper. Good.
Yes.
Okay, nice examples. So today is a new class. We've never done it before. Looking ahead, next week I'm going to talk about applications, implications, final projects. The week after that is managing invention. These aren't new technical topics. It's time to work on the final projects. Today is a crossover. And again, it's a new class we've never done before. And it's about system integration. Many final projects, I would complain that if we go back to, I've shown this a few times today, and I'll show it one more time. In the final project, I want to see each of these skills, but not separately. You need to integrate them. And in the final projects, I would often complain about the integration. And so we've rearranged the schedule to have a class just on system integration. And so first, let me illustrate what you could call disintegration. And rather than picking a particular student's bad project for this week, excuse me, this is an example with Midjourney, where I asked Midjourney to give a picture of a sloppy Fab Academy final project with loose circuit boards and a tangle of wires in a laser cut container made with poorly fitting finger joints. So This is what Midjourney came up with. And so this picture doesn't exist in reality. This is a Midjourney picture, but it's similar to many bad projects we've seen over the years. So this has all of the attributes of what we don't want for a final project. So the circuit boards are loose and rattling around. The wires are just tangled up, and it's in a really sloppy box. Pablo wants to know, does it work? I didn't ask if it works or not. And although this is sort of a joke, it's sort of not a joke. This isn't that far off from terrible final projects over the years. So this is what we don't want you to do. Then for what we do want you to do, the assignment is design and document the system integration of your final project. And what that means is not just the separate parts, but how the separate parts come together. And an example for this week that I like is this assignment made a robotic scoreboard. In the final project, it's nicely organized through all the stages of the final projects. In the electronics unit, here's the bill of materials. Here's how he's making the parts. Then here's the layout of the wiring. And then this is a picture I particularly wanted to show. This is really at the heart of this week. You see this beautiful design where he's designed how all the parts come together and get connected into a system, and then nicely documented all of that. And all of that's along the way to finishing the project, showing the whole integrated system. So it's a really nice example of integrating and finishing a final project. So to do system integration, you need to design the system, of course. And this first link is the history of design at Apple. And the reason I'm showing it is there was a battle between Apple computers and IBM family PC computers. The PCs generally just made boxes, and Steve Jobs invested very deeply in design. And the end result was Apple became the most, at one point, the most profitable, the most valuable company in the world. And essentially all the companies that were making PCs, they became commodities, and the businesses failed for all the leading ones, and they're produced as commodities now. And so this is a nice tour through making things look nice isn't just a Band-Aid on the surface. It fundamentally changes how you interact with it. And the diverging history of the success of Macs versus PCs was an important historical exercise of why design matters, making things that are beautiful and useful. In design, a while back, we did an experiment at MIT to teach. We had how to make almost anything. This was a class on how to design almost anything, on design practice. And you can think about design as progressing from conceptual design, where you think of how you're going to do something. Preliminary design is where you break it into what goes into it. And then detailed design is the actual implementation of it. But each of the stages are important. If you do detailed design prematurely, you freeze in design decisions that may cause serious issues. UX, or user experience. Jan is a Fab instructor, guru, colleague. This is from a recitation he did a few years ago on classic principles of design. And some of the points to keep in mind as you design your system obvious one is simplicity. This is a really important one. So visibility and feedback. So he has this hair dryer where there's this button and it's not clear what those symbols mean. And if you look at this, it's not clear, does this mean it's on or it's off? As opposed to one where it's simply aligned, it's easy to interpret what it's doing. Natural mappings. I noted before I wanted to close a website and I couldn't find where to do it. It was because the button to close the website wasn't near the website. Natural mappings are having controls near where you expect them to be. And again, in the bad hair dryer, the mappings, that way is fast, slow, this way is fast, and they're in opposite directions as opposed to a natural mapping. Using symbols that make sense in a language the user speaks as opposed to mysterious symbols. Avoiding modes where you need to know what state the system is in are all classic lessons in building user interfaces. This is from the machine building class from the Hamburg group, summarizing classic principles in building good user interface. Yeah, the recitation, Jan is him, that was in, he does a nice exposition, that was in 2021. Design, or maybe it was 2022. Let me see. No. Okay, good. Here it is. Copy link. Here's a video to Jan doing that. This is a recipe from the machine building class. The Hamburg group did a nice tour through principles for good interface design. That these are similar to the principles Jan is describing about just recurring lessons to make systems that are easy to understand and easy to use. So once you've designed a system, DFM is a key concept for, you want to design it to be manufacturable. And this is a guide through principles in design for manufacturing that echo some of the principles of design for users, but now it's viewed from manufacturing. So one is using a core set of standard components, avoiding unusual components. Net shape is using processes that produce parts in their finished form, not in ones that need a bunch of post-processing. A really important one that I've stressed before is worst is adhesives, because you can't undo an adhesive easily. Better is fasteners, but there's a lot of labor to put fasteners in and fasteners out. And better still is eliminating fasteners with just things that snap together and unsnap. And that makes, it reduces cost, it makes production faster and easier. You want to eliminate the need for careful alignment. So the classic MTM snap is based on these self-aligning features. And let's see, I'll come back, I'll talk about that feature in a little bit when I get to failure. Another DFM principle is minimizing parts. So Tesla has helped introduce what it calls gigacasting, which is making a few parts that you can assemble that replace many smaller parts to make the whole car, to make it cheaper and faster to assemble. That's been an important part of their cost reduction and production speed up. And another part of DFM is what process you use. So this is a video from Formlabs that just introduced a new printer. And in their printer, what they do is a comparison between an injection molder and a 3D printer. It's a little bit unfair because this is biasing it towards the printer, and there are other injection molders that could change the calculation a bit. But the point of this is for up to medium quantities, it's actually faster in this example to have a small print farm compared to going right to industrial production with injection molding. And so choices like between injection molding and 3D printing are a non-trivial trade-off for transition to production. And again, this is the new Formlabs printer that's a much faster parallel exposure. So those are some notes on you're designing the design. You want to design it to be usable, and you want to design it to be producible. And then when you're done, the design includes the design files. You want a bill of materials of what goes into your design. And this is a plugin for KiCad that can generate a bill of materials. You want to document how you produce it. And so again, from the Hamburg group, this is a really nice project that automates the production of assembly instructions. And then finally, you want to document how to use it. And former students started How-Toons that does this sort of documentation in cartoons. So your documentation doesn't need to be boring. It can be beautiful and expressive and fun. And How-Toons is a nice example of that. So all of that is just, we could do the whole semester on design. Those are just some principles that go into designing your system. Okay, next you need to do the packaging. And so packaging includes, you need to figure out how the PCBs, how your electronics gets mounted. And you can mount them on standoffs. You can have clips holding them. You can insert mold them. We've covered many different techniques, but just how the electronics gets assembled is an important part. You need to design where the wiring goes. And so the example I showed you in the featured project is a beautiful example of designing the routing of the wiring. You need to align the mechanisms. And so a simple example is when you build the Prusa, there's a key stage right here where you see there's a little slot there. And that's because once you assemble it, there's a little bit of uncertainty in the motor position to have the right belt tension. And so part of the assembly process is adding this degree of freedom. So you put it all together and then you tilt it a little bit to have the right tension on the belt, and then you tighten it. But the assembly process anticipates the degrees of freedom you need for the mechanism alignment. And then a recurring feature of bad projects is terrible surface finish. And so let's see, in Skylab was a nice example of just molding and casting week. They started with a average quality FDM print where you can see the printing. But then they did a nice process of using a UV resin and baby powder and using that fill in. And now at this point, you have this beautiful surface finish that's nice to look at and nice to hold and smooth. And so just spending some time on the surface finish of the part, goes back to the difference between the Mac versus PC trade-off. So you need to design, you need to package. Then testing, you need to test to make sure that it works. And that sounds obvious. You test to see it works, but industrially, a great deal of effort goes into testing. So QA is quality assurance, and quality assurance is preventing defects from coming in. So testing parts, making sure processes stay within specs, steps like that. QC is quality control, and that's testing that the output works. And so if you have an array of solenoids, making sure every solenoid is working. Now, to do those, it's more than just turning it in. Not all, but many systems, the properties change a little bit under operation. So when you start running a machine, the belts slip a little bit. When you heat up components, the values change a little bit. So burn-in is just leaving your system running and giving it time to settle, and seeing if it's going to fail when you leave it running. Many, not all, but many systems, the most significant stress is when you add power and take power away. So like solenoids energize and there's some force and it comes away. So cycling is you keep running the system up and down through cycles. Most labs can't do this, but industrially, environmental testing is running it through the highest temperature, lowest temperature, highest humidity. And then a very interesting kind of test is called fuzzing. And this is related to security vulnerabilities I'll talk about. Fuzzing is you take your system and you just give it random inputs. You spew garbage at it, and you see if you can make it go crazy by giving it nonsense inputs. And lots of faults are found that way. And in particular, many security vulnerabilities, which we'll talk about in a minute, are found from fuzzing. So all of that goes into a surprisingly common failure mode is you finished your final project and it worked for you, but when it's time to present it, it stops working. And so testing is an important part of that. And now we get to the heart of today's class, which is on how systems fail. So the goal of good system integration is to anticipate and protect against all of these failure modes. And every line I'm going to go through now is embodied in how projects have failed. And so these are each things to anticipate. So first one is, remember when I talked about stress versus strain on a material? A stress strain curve looks like this. Stress, you're pushing on a material, and then strain is how it's responding. In this range, it's linear, it's elastic. Out here, the material fails. But in this regime here, what's happening is it's no longer elastic. And so here, if you decrease the force, you go back to where you were. Here, if you decrease the force, you end up in a different place. And that's because you've deformed the material. And so it might still stay together, but you've changed the mechanical properties and you've changed the dimensions. And so keeping loads in the elastic limit is very important. If a material is going to fail, a common failure mode is, let's say I just have a joint. If you have a sharp corner and there's a load on here, it's going to crack here. This link is to, this is a paper from my lab on simulating physics. And the reason I'm linking it is just one of the examples here is this is modeling how this part's failed under load. And the color is the strain field. It's the load inside the material. And you see how it's concentrating around features. And then there's a crack that propagates through there. And so the lesson there is for parts under load, you want to avoid sharp features. You always want to fillet these that spreads the load out, that keeps it below the threshold where you get crack propagation. This is a link to the review of the original MakerBot. And Bree Pettis describes this machine as on-the-job training for mechanical engineering. And it was full of poor decisions for at this stage in his career. And so, let's see. If you zoom in on right here, you'll see there's a bolt and a nut. And the only thing holding the nut in place is just the bolt screwing it against the wood. And as this printer printed, those bolts would walk and slowly the machine would disassemble itself and loosen up. There was nothing keeping the nuts and bolts in place. And so you want to load, if you're using fasteners, you want to load them with thread locks so that they can't walk. So you can use lock washers, you can use insert nuts, but you want to have a loading so that vibration doesn't walk your fasteners. Let's see, I'll add, it's a good idea if you have bearings to preload them. Unloaded bearings rattle. Bearings are happier when there's always some load on them, so they're always in contact. Stripped threads are the bane of things like little set screws and collets. You want to avoid tiny threads that are easy to strip. Misalignment, if you look at the machine, in the first version of the machine, you'll see the rails are just here. And when Jonathan and Nadia made the machine, it worked great, but nobody else could reproduce it. And then in the revised design, if you look right in there, there's a flexure. And what the flexure is doing is, unless the machine making this is perfectly aligned, the rails on the two sides can be very slightly misaligned. But if the rails are misaligned, it means the carriage binds and just doesn't move. And so the very small flexure just has a fraction of a millimeter of travel, but that little travel accommodates for misalignment in the rails and prevents the machine from locking up. And then finally, for mechanical failure, you can have static failure from overloading. You can also have dynamic failure. And probably the most famous one in history is this bridge that collapsed. There's great videos of this. The bridge wasn't quite stiff enough, but it was fine under a normal load. They tested it. The bridge was strong enough it would hold up cars. But what they missed was the wind going through the wires would make an oscillation. The oscillation would couple to the bridge that wasn't quite stiff enough. The bridge could rock back and forth just a little bit. And then there was a resonance, like pushing a swing between the guy wires and the bridge. And the oscillations got bigger and bigger and bigger. And eventually the bridge fell in the ocean. And so that's an example of, you wouldn't see the failure in static testing, but the failure came from the dynamics of the system. Okay, so all of that is just mechanical failure. Then wiring failures. So a surprisingly common one is ripping up traces. The printed circuit board is a laminate. You solder to the traces, but if you pull on something connected to it, it's surprisingly easy to beat the glue holding the copper down and rip it up. It's easier on the machine ones, but even on commercial PCBs, if you pull against the traces, you can easily rip them up. Another one is we have connectors, but if you pull on the connector, depending on the connector, it can be easy to pull the wire out of the connector. So all that adds up to strain relief. These are all parts whose job in life is just simply to handle loads on connectors. When you have wires going into a connector, you want to clamp the wire. So if you pull on the wire, you're not pulling out of the connector, or you're not ripping up a trace. You're just pulling on the wire. The simple headers we use are unpolarized, which means you can connect them the wrong way, which I'll talk about. Generally, it's good to use polarized connectors that only have one way to connect them, or to make connectors that are symmetrical. So if you connect it the opposite way, you have enough pins like USB 6 that any orientation works. This next one is this airplane was lost and everybody died. And it was because of wiring. So Kapton is a wonderful material that's strong, that withstands high temperatures, and has all sorts of use cases. And there was a time it was used for insulation and wiring. When wires rub, they can get cracks. They abrade, and it can remove insulation, and they can get cracks. Dielectric breakdown, we saw that in output devices. It's about a kilovolt per millimeter, and less than that for less than a millimeter. That's what you need to actually short circuit through a material. What happened with the Kapton wiring is, as it flexed and was rubbed, cracks would propagate and open up a little bit. As the cracks open up, it made it easier to have dielectric breakdown and have a discharge, like between a wire carrying a voltage and ground around it. And then it turns out Kapton had a terrible property, which is similar to graphene, if you've heard of that, which is once it starts to discharge, it carbonizes the Kapton, and it turns it from an insulator to it becomes a conductor. And then once it becomes a conductor, you can start to discharge through the whole wire, and sort of the whole wire becomes a conductor. And all of that led to a fire in the wiring in the plane that took it out of the sky. So Kapton is no longer used for wiring insulation, but there are many different failure modes of so yeah, Ricardo said they skipped environmental testing. Ricardo, that was done to test it, sort of in the factory. What they didn't anticipate was lifetime, what was, many months of rubbing and flexing. And so they didn't test against that sort of lifetime scenario. That wasn't anticipated in the environmental testing. So there are many different failures that come from wires rubbing and abrading. So one implication is if wires are moving, you want to guide them. This is my student, Jake. One nice technique he does is he just uses a tape measure in a sleeve to make a flexible wire guide. You can 3D print wire guides. And let me go back to this picture here. So, yeah, the Svavar 3D printed a wire guide like this. So this lovely picture is in this final project. He's laying out the wiring to connect all the parts of the system. In Airbus lost $1 billion from getting that wrong. Literally, it was $1 billion failure. And so Toulouse was building the A380. The German part of Airbus was making the wiring harnesses. They brought the German wiring harnesses to the French airplane, installed them in the airplane, got to the very end, and the connectors didn't reach each other. And it ended up being $1 billion failure to figure out why the German harness didn't fit the French airplane. So, designing the routing of the wiring through your system is a very important part of system integration. So then, component failure. A common failure is blowing out power transistors. So the power, we saw the Braille project that has the array of solenoids, with a power transistor on each one. If you put too much voltage, too much current, or go too far out of temperature range, you'll blow out a power transistor. And it's a common failure mode that your project is working, and then when you demo it, it's not working and you've blown a transistor. One of the most common ways you blow out a power transistor is a motor acts like a coil. When current's flowing through it, there's a magnetic field. When you open it and you stop the current flowing, the magnetic field turns into a big surge of a reverse current that can easily go way out of voltage range and blow out the transistors. And so a common way you do that is to have a diode that prevents current going the wrong way to protect going out of the voltage range. Another sad failure mode in final projects is if this is a voltage regulator, this is the input, this is the output. If you connect the supply with the wrong orientation, you'll kill the regulator. And so quite a few final projects have failed at the last minute because the power got connected wrong. So one way is to make sure you use a polarized connector. One thing you can do is you can just put a diode on the input to the regulator. Now, this is bad if there's a lot of current, because remember, power is current times voltage. And so if you have a lot of current, that means you get dissipation here. But if you're not drawing a lot of current, like just for a microcontroller, this is a safe thing to do to protect your regulator from regulator from being connected backwards. Then on your processor, they have a voltage, maximum voltage. If you go over the voltage into the processor, you'll kill it. But it's also a key spec is the current you can get out of a pin and the current you can put into a pin. If you have a 0, that corresponds to ground, which means it's a sink. If you try to pull too much current from a pin, generally it just droops. But if you try to put too much current in a pin, you can kill the processor. And so one thing you can do that's also related to current limiting is you'll often see on commercial products, you have whatever it is, and then you have the connections to the outside world. And then you'll see a small resistor here, like maybe 100 ohms. And what that resistor is there for is if something bad happens in the outside world, like you short these together, or you connect power to a logic pin, this resistor here normally isn't really doing anything, but it's protecting so you don't blow up the processor if you connect it wrong. There's a whole family of parts. These are transient protection diodes, and their job is just to quickly switch to prevent big spikes from coming in for things like, if there's a lightning storm, if there's a glitch in the power supply. And then if you have low-level signals, they can easily be swamped by high-level noise. The copper tape we use to vinyl cut, one common use for it is making pockets in electric guitars. The pickup from the coil on the electric guitar is a very low-level signal, and it picks up noise from things like fluorescent lights. And so making a shield of copper tape around sensitive electronics significantly reduces the noise from the environment. So those are all ways components can fail. Then power can fail. So for your project, you should do a power budget. For the Braille, I gave the example, you want to figure out how much current you need from each solenoid, and then how much current your supply can provide. A power supply, you can think of it as an ideal battery that's a voltage source with a resistor inside. And this resistor is the output impedance in the supply. And for a good supply, it's small, but for a bad supply, it's large, which means when you start pulling current, there's a voltage drop across this resistor and the supply voltage droops. And this can be really nasty to debug because when the supply voltage starts to go down, the processor can still work, but it's not working correctly. It's not right in the head. And you can get nonsense behavior that makes no sense because it makes no sense, and it's just because the power is drooping. Likewise, batteries, if you're using them, have a lifetime, which sounds obvious. But I've seen many projects spend a lot of time debugging weird behavior that just corresponds to their batteries dying. And batteries unloaded, you'll measure the voltage on the battery and the voltage is fine. But because the battery is dead, as soon as you pull current, it drops way down. And so even a small drop in a battery voltage means that you're going to get a big droop when you have loads from it. This was a classic in both power supply and bad design. This is the Lunyi machine at the instructor boot camp in Leon. A group of unnamed instructors were setting it up, and I was over at another side of the lab, excuse me, and then there was a very characteristic sound, pop. And once you've heard it, you get chills when you hear that sound. There was a pop and a little puff of smoke. And what had happened was, in connecting the power supply to the control electronics, there were two places you plug it in. They both looked the same. And in tiny print, one said 48 volts and one said 24 volts. And the unnamed instructor connected the 48 volt supply to the 24 volt input and blew out the power supply. So the wrong voltage obviously can blow things out, and that was a let's see, there's a link in the chat to Magic Smoke. it was a classic in bad design because you had to look really carefully to realize that these two things, one of which would kill the supply, were right next to each other. If you have a motor connected to your power supply, every time the motor commutates, you get a glitch on the rail. And if you look on an oscilloscope, you'll see spikes on the power line. If the spikes are big enough, they reset the processor. And these are really hard to debug because the processor is mysteriously doing crazy stuff because it keeps getting reset. So power supply noise can give you software faults that have nothing to do with your code. Your code is fine. The problem is you're getting software faults from glitches in the power supply. As wires get long, the resistance goes up and the inductance goes up. The inductance means things happen slower. So something that works with a short cable can fail with a long cable. I've mentioned before bypass capacitors. So if you have a power supply over here, and then the wire is going to a processor here and a processor here, they both need bypass capacitors right next to them. And the reason is the wire itself has a lot of inductance. And so this bypass capacitor doesn't help the processor here. You actually need physical proximity. And these capacitors are both storing charge to help the processor, and they're coupling noise into ground. So they're a really good practice. And then another good practice that I had mentioned in is all of your grounds should be tied to a single point. That if you have grounds scattered all over the place, and remember there's resistance in the ground wire, current going through the wire means the ground voltage here is different than the ground voltage there. So what you want to do is, as much as possible, if you have loads in different places, you want to separately tie them into a ground mecha, not connect them to each other. It doesn't matter for low currents, but when you have bigger currents going through grounds, let's see, did the unnamed team actually document blowing up the machine? Was that in here?
Yeah, it's a
It might be in-
but it is.
Okay, good. Yeah, I actually I don't say it here, but it's an important point that it's important to share failure modes to learn from them. Okay, so these are all ways power can fail. Then comes software failure. Memory leaks are really nasty. This can be why over time your phone or your computer starts doing crazy things and you need to reboot it. Memory leaks happen when you allocate variables. So to make a reading, excuse me, you allocate a variable, but you allocate the variable every time you make the reading. And so just bit by bit, you're eating up the memory. And eventually, when the memory gets low, the system goes crazy. And so, let's see, I'll add a note. You need to be aware of where you're making things that consume memory but don't free it. Garbage collection is a thing some languages know how to do to recover memory. Buffer overflow has led to huge amounts of damage. This is let's go back to the programming class. Or no, let's see, the high-level programming class. So I talked about C, C++. Then I talked about languages like Rust. A key thing they do is in C, you can allocate a buffer to store values, and you can write data in or you can read from it. But it doesn't prevent you from either writing data beyond the end of the buffer or reading from the buffer going beyond the end of it. So Heartbleed was a bug in SSL where there was a simple heartbeat you used to keep a secure connection open. And there was a simple query response where you would send a query and it didn't check the query versus the buffer size. And SSL, which is the bedrock that's used, when you go to a website that's SSH and you get the padlock that says this is secure. This is when you give your bank account information, your private security codes securely over the internet, all of that is going over this transport. And it turned out, let's see, Nicholas is adding a XKCD cartoon on, yeah. Nothing was checking that you're asking for too many characters, and you could read memory that you're not supposed to see. And in that memory, you could get all kinds of valuable data by just repeatedly pulling memory from a server you're not supposed to see. All of that came from a simple buffer overflow failure. The fix for that in a language like C is you need to check for buffer overflow. You need to check that queries don't go beyond the variables they have. More recent languages automate that prevent you from being able to do that. Race conditions can be really nasty because it can be hard to tell they're there. A race condition is your code implicitly assumes something happens before something else, but there's nothing to enforce it. So like you assert something on one pin, you read something on another pin, and you assume the timing happens in that order. But unless you explicitly account for it, it turns out you can have two things that are close to each other in timing, and because of things you don't control, one may happen before or after the other. So a race condition is making sure sequencing you assume happen in the same order. Variable scope is you have variables and you have modules, and in a way you didn't anticipate, two parts of code are interacting with the same variable, even though they think the variables are private to them. And so for that, it's really important to package code into objects that have well-defined interfaces, so code outside can't mess with variables inside. Then dependencies are just in this class, we heard about pip install packages or npm install packages. The packages you're using to do the work in turn depend on other packages, and often you don't have good visibility into that. And this was an example of a JavaScript package in npm that had a bug that let remote code be executed on a server. And it was deployed millions of times. and had a simple failure in checking that allowed for remote code execution. So terrible vulnerability. When you build your code, you may think you're doing everything very carefully, you're checking everything, but a lot of vulnerabilities come in from unanticipated ones underneath it. And historically, in the history of the internet, OpenSSH, for example, these libraries that are underneath core functions, many of them were run as open source projects with just a few developers, and then billions of dollars of businesses depended on them. So it's important to be aware of vulnerabilities that come in your code that didn't come from you, but come from the packages you're pulling in. And a final note on software security is security through obscurity is you keep stuff secret. And that sounds obvious, but overall it has a terrible reputation because there's all sorts of systems that were thought to be secure that had vulnerabilities. At this point, almost always what's preferred is security through transparency, where all of the code is public and the only thing that's secret is a well-defined secret, like a key for authentication. But you openly share how you're protecting yourself, which makes it possible for anybody to find vulnerabilities in it. So there's some debate about the relative balance in these, but most of the core security code now is open, so anybody can see it, can attack it, and you just carefully protect individual pieces of information. So those are all some of the ways software fails. Then there's a note in the chat that's a good lead-in, which is see, the original Tetris crashes when you get to level 155 due to the game's score counting algorithm that becomes too heavy. So so this is a class I teach on mathematical algorithms. O of notation is how hard the algorithm has to work for how big the problem is. So O of n means the difficulty increases proportional to the problem size. O of n squared means it goes as the square of the problem size. And so, for example, multiplying a matrix of a vector times a matrix of size n is order n squared. And that quickly becomes infeasible for a large problem. So the fast Fourier transform reduces that problem from n squared to n log n times log n, not n squared. And that difference is essential across signal processing. And then the worst algorithms are exponential. And so there are many examples of things that work on small problems, but as the problem gets bigger and bigger, it fails because of the scaling. So it's important you understand how the work your system does depends on the problem size. And in fact, this is a paper written by a colleague on phase transitions in computational complexity, where this is how big the problem is. And like, let's say this is the United States. And you're a salesman and you need to visit a series of cities and you want to find the best route. This is how many cities there are. And this is how hard it is to find the best route. You might think it just keeps getting harder and harder. But in fact, it actually looks like this, where when it's small, it's easy to figure out because there's just a few cities. When you have to go to many cities, it's easy because all routes are good. You just go everywhere uniformly. And in between are the hard problems, and in between they get extremely hard. And so there's a very interesting and not obvious literature in how the difficulty of solving problems depends on the size of the problem. And so, we saw these surgical tools, and an example of this would be how well the algorithm performs versus the number of different surgical tools you need to distinguish for the scaling. So supply chains can fail. In COVID, auto factories were shut down and lost billions of dollars. And those weren't over giant GPUs. Those were not metaphorically, but literally over chips like the motor controllers and the microcontrollers we've been using. Those very simple chips we use to control a stepper motor, the supply chains failed in the pandemic, and whole car companies had to shut down because they couldn't get the chip. It's surprisingly common to have your project done, everything's working great, you're happy, everything's beautiful, you want to create a business around it, and then suddenly you can't get a key part you need. It happens surprisingly often. And so the supply chains failed in the pandemic for a series of pandemic-related reasons, but more commonly in things like chip fab, there's a boom-bust cycle. And so initially you start producing something, and that's great. And then the demand starts increasing, so you produce more, the demand is increasing. And then at some point, you start to satisfy the demand. And now you're producing too much. And so you have a glut of inventory, and so you start decreasing your production. But meanwhile, the demand is still going. And now this means you can't get the part. And so here you're struggling and maybe designing around a different part. Here you're clearing the inventory. And then here you start producing again, but meanwhile the demand is falling. And so now you're producing parts, but there isn't the demand for them. And so chip fabrication has been notorious for these boom-bust cycles, which can mean you need to design unexpectedly around a different part. It can mean you need to maintain an inventory of parts you don't think you need, but you keep a stash to be safe. And so it's very frustrating for that. Actually, let me add, there's a category I didn't add, which is when all of that's done and you're producing and everything's great, another common failure mode is financial, which is just cash flow. Actually, I'll talk about this in the Invention Week. This is, you've sold lots of products, everything is going great, but the business is the payment is out of phase with your production. And I'll talk about that in the Invention Week. Collaboration itself introduces a vulnerability. So a very famous example was NASA sent a fabulous spacecraft to Mars. Everything worked perfectly until it crashed into Mars. And it turned out that between the team that built the spacecraft and the team that was operating spacecraft, there was a disagreement over English versus metric units. They were operating in different units, and the command made no sense, and the spacecraft crashed. Whole mission lost. And so when you collaborate, there's vulnerabilities that come in exchange between the collaboration. And in particular, as much as possible, it's really important to work in common environments. So in the Airbus example, the German team was using a different design tool from the French team, which is how they could diverge. Same sort of thing happened in the NASA Mars orbiter crash. You want to try to collaborate using, it sounds obvious, shared tools in a common environment, but billions of dollars have been lost from that. And then in talking about failure, Boeing has been building the Starliner. SpaceX has been building the Starship. Boeing's Starliner is a decade late and billions of dollars over budget and has yet to fly an astronaut. SpaceX's Starship has been doing great, even though it keeps exploding. And so this is a nice explanation of SpaceX keeps testing them and they keep exploding. And every time they explode, they get data from it. And so Boeing is doing a classic example of linear development, of you design the project and then you fly it at the end. SpaceX is doing a classic example of running in spirals. Each time they learn a little more, they improve it a little bit. They have enough budget that they can afford to blow them up. But the difference between the success of their rockets and the failure of the Boeing and United Launch Alliance rockets is a classic example of feed forward versus feedback in design. So for your final projects, you don't want the system integration to happen the day before the final exam, the final presentation. You want to keep building your system and keep testing it and keep failing it as it matures. So finally, once you're done all of that, increasingly there's legislation about a right to repair. And this is a public interest group working on right to repair. So increasingly there are laws that you have to be able to fix what you own. To be able to repair it, you need to be able to disassemble it, reuse parts. And so the good design principle that I've described on just design for manufacturing and modularity in design also are important for life cycle, because it means you can disassemble and reuse the parts. And then the recycling comes at the end. Increasingly, the EU has laws that you need to take back products at the end of their lifetime. So you need to design anticipating recycling and reuse. What parts can you recycle? What parts can you reuse? So increasingly, you can't just produce something and say it's somebody else's job to get rid of it. You need to design against the whole life cycle of the product. How is its end of life gonna? How is it gonna get repaired? And then how is it gonna get recycled? So if we go back to this project, let's see, I think it was in Italy in 2016. I don't know what happened to Caputo Gianfranco, but if you go to his site, the final project site is a classic of a good site that goes through all the stages. And in the presentation, you'll see everything I'm describing of a beautifully finished, let's see. So it's beautifully finished. It has a straightforward, easy to understand interface. It looks great. And if we go back to development, so just the electronics page shows these core things of here's his bill of materials. Here's the design of the parts. And then he's thought really just carefully, it's not a huge amount of work, but laying out how all the parts come together in a system. And so it's just a classic example of doing good system integration. So the assignment is to design the system integration in your project. And so that means the overall design, what are the subsystems in hardware, software, form, function, mechanism, and how do they fit together as a system? So how are wires routed? How is electronics mounted? How are mechanisms aligned? It's the design not as separate files for each subsystem, but the design of your project as a system. You know, think about good design principles. This was just a quick taste of it. Think about packaging and surface finish. And then a big part of this exercise is how are you going to test your project? And then looking at doing good design. Each of these failure modes has ways you avoid them. So stress concentration means you fill it corners. Blowing out transistors means you have protection diodes. Every one of the examples I've described has both led to commercial failures, and we've seen all of these in final projects. And then I do want you to describe, so you need to do this for your final project, but as a separate assignment for this week, I want you to document how the final project is integrated. So I want you to document what are all the systems and what are all the subsystems and how do they come into a system. You need to do this for the final project, but this assignment is to force you to do that. And this is all leading up to this is what success looks like, and this is what failure looks like. And again, this is mid-journey, but this is surprisingly close to some of the worst projects we've seen over the years, of a sloppy box barely held together with a tangle of boards and a tangle of wires that might have maybe worked once, but this is what we want to avoid. And so for this week's assignment, design and document how all the elements you're working on come together in a complete system. So that's system integration. And then next week, I'll talk about what can you do with all these skills and what good final projects look like. The week after that, I'll talk about the whole life cycle of invention, no new technical comments. And then we're up to the final presentations. So the goal this week is to give you a whole week dedicated to system integration. And so design it and get working on implementing it, hopefully raising the boundary and the barrier to have fewer ugly projects and more beautiful projects. And think back to Apple versus PCs. Do you want to be commoditized and driven out of business, or do you want to become the world's most valuable company? Was a historical lesson about the value of good design. So that's a tour through system integration. As usual, we have the great Saturday open team. Take advantage of that. There aren't enough students using it. You have great expertise to help coach. No recitation coming week. And then in 2 weeks, recitation will be on startups. Okay, I'll be interested to see how you do. This is a new week and it's a new assignment. And so I'll be interested to see how you do with it, with designing and documenting complete systems, not just scattered parts. And with that, have a good week and see you all next Wednesday. Bye-bye.
Bye.
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 Bye-bye, Neil. Bye-bye.
Assalamualaikum. Ciao. Ciao.